All right, let's continue with an example before your next exploration, and you try just to bring that similarity back. So find the unknown lengths in the pair of similar triangles. So they say that they're similar, and they're not drawn to scale. Assume corresponding sides are in the same position within each triangle. So they're telling us like, hey, this corresponds to this and this corresponds to that, which is great because sometimes it's really hard to tell, and they should tell you. So what we're going to do here is we're going to set up some proportions so that we can see what's going on here. So 21 corresponds to 7, and 21 corresponds to A. You might be like, oh, I already know some stuff, and that's fine. Make sure you keep, this big triangle on top, big over little. It's important to keep it the same. B over 8.5. So now let's see if we can see what's going on here. It's pretty clear that these are the same side lengths, so A is going to equal 7. Okay, so we're halfway done. But now we've got to figure out what B is. So there's a couple different ways to do it, but let's use the internal factor. So we've got 21 over 7 is equal to B over 8.5. Let's look at the internal factor. And what I mean by that is let's look how these fractions relate to themselves. So I have B here, and I want to know how to get 8.5 times what, right? So I'm going to do, 7 times what? 7 times 3. So 8.5 times 3. So B is equal to 8.5 times 3. B is equal to 25.5. Okay, so I've got that. I think that this is more efficient than if we were to use a scale factor. Doesn't mean it's right, but let's look at a scale factor for a moment. If I was to find the scale factor, using the scale factor method, I would need to say, okay, how do I get from 7 to 8.5 times what? And that's fine. I can do that. Get my K value, and then that's what I'm going to multiply this way. That's fine. But because I know the relationship between 21 and 7, that's why I decided to use internal, because I knew that 7 times 3 is 21, and 21 divided by 3 is 7. So you can make decisions based on what you already know. Is this harder? I don't know. I think that this is more efficient, but for some people, they want to learn one method, and that's okay. But having these different methods and understanding when might be more efficient than another is helpful for your student. All right, go ahead and give these a try. Make sure you're following the directions and doing these in different ways. And then press play when you're ready to see the solution. I encourage you to pause here and read these from your textbook. These are really great stories of how to make connections with similarity and the importance to do so. And then here's another one as well. Okay, let's do some more examples. So triangle ABC is similar to DEC. All right, so triangle A, just make sense of it, ABC is similar to DEC. Okay, so this is the first time we've seen this split triangle. Find the length of X. All right, so we need to set up proportions here to help us make sense of this. So our triangle ABC, what do we know? Well, we know the length of AB, and that's related to the length of DE. So we know, and I'm just going to put like big over small to help me here. We know that 12.35 is related to 1.9. Those are similar sides. And so this full length here, X is a part of the big triangle. It's BC. And so that's related to this side length here, 1.3. And in this case here, I don't think that there's maybe one particular method that is more efficient than the other. So I would say, let's just try the scale factor, because I think we did the internal one last time. So scale factor sends us from one fraction to the other. So I'm going to say, okay, I really want to know 12.35 times what? So I'm going to go in this direction as well. It doesn't really matter. So 1.9 times k is equal to 1.3. So I'm going to divide both sides by 1.9. And I get k is equal to 1.3 divided by 1.9. And my fraction gives me a long decimal. I'm going to turn that back into a fraction. And I get 13 over 9. So that's what I need to multiply this by, 13 over 9. So 12.35 times 13 over 9 is equal to x. And when I type that into my calculator, times 12.35, oops, 13 over 19, I've got it in my book, but I can't read my own handwriting. I get 8.45 is equal to x, and that's meters. So that means this is 8.45 meters. And again, you could have used scale factor. You could have said, okay, I want to know how do I get from 1.9 to 12.1.9 times what gives me 12.35, and that's going to be the value I multiply by 1.3. You can do that too. Let's look at another example. How high is a tree that casts a 39-foot shadow at the same time a 5-foot pole casts a shadow which is 12 feet long? All right, let's take a peek here. Let's draw it out. Okay. How high is a tree? And we can actually, we'll go one step further. Let's call it x. We don't know. That casts a 39-foot shadow. So that's 39 feet. At the same time, a 5-foot pole, so we know that that's 5 feet, casts a 12-foot long shadow. All right, so we've got the height here and the shadow. So we've got height over shadow. So we've got x over 39, that's the tree, and that's equal to the pole, and the height of the pole is 5, and the shadow of the pole is 12. So I'm going to use the scale factor here just because internally 5 times what gives me 12, I don't know, so, or 12 divided by what gives me 5, so I'll just go across. Scale factor. So 12 times k equals 39. So k equals, let's just keep it as a fraction, 39 over 12. So that means I need to multiply this also by 39 over 12. So x is equal to 5 times 39 over 12, and that's going to give me 16.25. So the answer here is 16.25 feet. Go ahead and give these 2 problems a try. Press play when you're ready to see the solution. And that concludes the section.